All right, you guys, welcome back for part 3. This is our final part of this lecture video. Now, we have talked about these rules for derivatives, and while all of these are really great and useful for a polynomial, we know polynomials are not the be-all end-all of functions. We know there's other functions out there. We're not going to get into rules for exponents. That's going to be another section later on. But what we are going to do is talk about what happens if we have the product or quotient of two functions. Now, unfortunately, this derivative is not something that's super simple and easy like the power rule where we just move one down and subtract. It's more similar to the sum and difference formulas of trig functions. If you remember, like things like cosine of alpha plus beta, it's kind of similar to that. And so let's just dive right into the product rule because there's really no reason to delay it. So the product rule, okay. Okay, why is this not working? Even at home doesn't want to work. There we go. The product rule. So, as always, we need to let f of x and g of x be differentiable. And I'm going to for some reason my pen is dragging. Just differentiable functions. Again, that just means we can take their derivatives, right? So if they're differentiable functions, then d dx of f of x g of x, so this is the derivative of the product, that is equal to d dx of f of x times g of x plus d dx of g of x times f of x. Okay, so that is if j of x equals f of x times g of x, then j prime of x equals f prime of x g of x plus g prime of x f of x. So what this is really saying, what this is really getting to is if we have a function is defined as the product of two functions, then the derivative of that product is the derivative of the first times the second plus the derivative of the second times the first. So that order is important, right? So we may think like, oh, it doesn't matter. Like I could do like the derivative of g times f plus derivative of f times g. And while mathematically that's true, it's going to behoove you for when we get into the quotient rule to keep this thought of as the derivative of the first times the second plus the derivative of the second times the first. And the reason you'll see is when we get to quotient rule that remembering derivative first times second, derivative second times first will help to make it so if you remember it that way, there's no mix-ups or any kind of extra confusions. So this can be really simple if we use just some really kind of basic kind of ideas. So we're going to use those rules we talked about in part 2, the power rule, the sum rule, difference rule, and constant multiplier rule. And so let's find this example. Let's find the derivative of, we'll call this j of x equals x squared plus 2 times 3x cubed minus 5x. Now, I want to do this in two ways. Okay, the first way we're going to do it is using what I think is probably the most simple way to do this, and that is to distribute and then use the power rules. So, let's see. First way, multiply and simplify. Then differentiate. So what I mean by that is we're just going to look at j of x, and we are going to do, take our x squared plus 2 times 3x cubed minus 5x. We're just going to do this little ordeal here. So we end up with x squared times 3x cubed gives me 3x to the fifth. X squared times negative 5x gives me negative 5x cubed. Then we have 2 times 3x cubed, which gives me plus 6x cubed. And lastly, we have 2 times negative 5x, so we get negative 10x. 3x to this, we're going to combine like terms. We have negative 5x cubed. Sorry, I'm just looking at my pen trying to figure out why it's doing this. We have negative 5x cubed plus 6x cubed, so the negative 5 and plus 6 become a 1, a positive 1, so we just get plus x cubed. We have our minus 10x. Now, we have that, so now to find j prime of x, we can use our constant multiple rule, our product rule, or our sum rule, our difference rule, and our power rule. So this first piece here, 3x to the fifth, we bring the 5 down, so we get 5 times 3 gives me 15. And then we take 1 off of the exponent. So instead of 5, we get 4. Our second term, we have plus x cubed, so we bring the 3 down, so we get plus 3x. Take 1 off the exponent, so instead of 3, it gets 2. This last one, we get negative 10x, so bring the 1 down, it goes, right? We can just kind of see this pattern. Bring the 1 down, negative 10 times 1 is negative 10. Take 1 away from the x, we get 0, and anything to the 0 is 1. So there's our derivative. Right, as I said, this is pretty easy, right? This is a function that this is probably the way I would go about doing this, just because this is pretty quick. You'll see that using the product rule absolutely works. It's just less. It's just more involved. So second way is the product rule. So we have that j of x equals x squared plus 2 times 3x cubed minus 5x. So this is not something you need to do. This is something that is maybe a good idea to kind of think of and just kind of keep in your mind. I'm going to explicitly write this out. So in this problem here, our our f of x is x squared plus 2. Our g of x is 3x cubed minus 5x. Now I'm going to actually erase this because there's something else I want to do. So I know I'm going to need this function, but I'm also going to need its derivative for this. So the derivative here, so derivative of x squared is 2x, and then plus 2, it's just, that's it. So there's our derivative. Now g of x is 3x cubed minus 5x. G prime of x, the derivative of g, we take our exponent of 3, and we multiply by the coefficient 3, we get 9x x, bring our exponent down 1 squared, negative 5x becomes negative 5. The reason I did that is if we look back at our power rule, right? J prime of x is f prime of x times g of x plus g prime of x, f of x. So I now have all 4 of those, and I just need to plug them in. So j prime of x is 2x times g of x, which is our 3x cubed minus 5x, plus g prime of x, 9x squared minus 5, times f of x, which is x squared plus 2. Now, you may think, well, hey, that's pretty quick, but notice the form, the j prime of x from what I did before to what I have now, right? These are not the same. They're equivalent, but right, I would much rather deal with the j prime of x that I got in the first way, but we're not done, right? We just need to simplify. But notice here, right, in this first problem, I did a binomial multiplication. X squared plus 2 times 3x cubed minus 5. Right? That product, boom, combine like terms, then really easy derivative. Here, not so much, right? Now we have to do, if you look at the second term here, the 9x squared minus 5 times x squared plus 2, that is also a binomial product. And so we end up with kind of doing more algebra than what we would have if we would have done it that first way. The reason I'm showing you this problem is because the derivatives of f and g are really easy to find and really quick, and we haven't developed the tools to use this in a better situation. And we'll show some kind of times when we want to use this and when we won't, especially as we develop more and more skills. The really important thing here with this chapter is to identify and understand what tools you have. So we're creating some tools with these differentiation rules, and to know when to use them, and to know where to use them, and to know when to use other things. And so that's the really important thing with this whole chapter. This whole chapter, we're going to be building up some tools, right? If you want to use the analogy of a toolbox, right? We're filling our toolbox up with tools. We've got some hammers in there, some screwdrivers, we've got some Allen wrenches, we've got all sorts of fun tools in there. And we need to figure out what to use for the right thing, right? If we're hanging a picture, we don't want to get out our screwdriver. That's probably not the easiest way. Let's say we're just hanging up a small, easy picture, right? Just nail in the wall, right? We don't need a screwdriver to put a nail in the wall. We want our hammer. Same way with a problem like this, I probably wouldn't use the product rule in practice, but I want to do it here just to show you guys what happens. So let's go through and simplify j of x. So we have our 2x, we need to distribute. So we get 2x times 3x cubed gives me 6x to the 4th. And then I have 2x times negative 5x gives me negative 10x squared. Now you may be going, well, I had 15x to the 4th and I have 3x squared, so those numbers aren't looking good. But remember, we have a whole other side to deal with. So over here I have my 9x squared minus 5, and I'm multiplying by the x squared plus 2. So we do all of these. So our 9x squared times x squared gives me plus 9x to the 4th. 9x squared times 2 gives me plus 18x squared. Negative 5 times x squared, negative 5x squared. And negative 5 times 2 gives me minus 10. So now we just combine like terms. Now the way I like to write this down, 1, 2, 3, 4. 1, 2, 3, 4, right? Those are our 4th degree terms. So we have 6x to the 4th, 9x to the 4th gives me 15x to the 4th squared. Negative 10x squared plus 18x squared gives me plus 8x squared. We have minus 5x minus 10. And that is not right. What's going on? You guys are probably yelling at me. Sorry, I'm looking at my notes that I've got written for this problem. Boop. There we go. So this is a squared term. So, sorry, there we go. So we're negative 10x squared plus 18x squared minus 5x squared. We get our plus 3x squared. Oops. 3x squared. And then our minus 10. There we go. All right, that's right. I can do math, I can count, I can add things. So we see that we get the same thing now. But as you can see, right, that was, I mean, I even made mistakes here and it took me a second to figure it out. This problem I would do the first way. But what if we had something like, let's say, this is going to be a, and my pen's not working again, because of course not. Why would it? There we go. Here's a future problem. Oh man. What if I wanted to find dx of something like e to the x times, say, okay, times 4x, there's 1 squared, 4x squared minus 3, right? In the future, we'll see that the derivative of e to the x is actually a really easy one to deal with, to work with, and we'll evaluate that when we get there. And then, 4x squared minus 3x is pretty easy, but when we combine these and you end up with 4x squared e to the x minus 3e to the x, it's not really a nice fun thing to differentiate. So this one here, we would definitely use the product rule. Okay, I want to do one more problem, and I want to think about this because this is something that is really important to understand. And we talked about expanding the like sum rule and difference rule and stuff like that. I want to talk about extending or expanding the product rule. So let's let j of x equal f of x times g of x times h of x, we'll say, where f, g, and h are all differentiable functions. So keep in mind, this means that we can take the derivatives of each one individually. Now, how do I go about applying the product rule? One way is the easiest way is, because we already have what to do with the derivative of f of x times g of x. So what I'm going to do is I'm going to treat this as two functions. So j of x equals f of x times g of x times h of x. I'm going to say this right here is kind of function 1, and this is function 2. Right? So remember, when we talked about the product rule, we said derivative of the first times the second plus derivative of the second times the first. So this means that j prime of x is the derivative of the first times the second plus the derivative of the second times the first. We know what the derivative of f of x g of x is. It is the derivative of the first times the second plus the derivative of the second times the first, and that whole thing is being multiplied by h of x. So if I distribute this h of x, what I get is the derivative of the first times the second times the third plus the derivative of the second times the first times the third plus the derivative of the third times the first times the second. So by expanding the product rule, we can see here what we essentially do is we take the product of each of the, or sorry, the derivative of the product, sorry, take the derivative of each term of the product kind of in sequence, multiplied by just the regular functions, not the derivatives of those, and we get this kind of massive thing. So if I were to have, say, 4 functions, say f, g, h, and k of x, right? Then we would say that's the derivative of f times GHK plus the derivative of g times FHK plus the derivative of f times, derivative of h times FGK, and then plus the derivative of k times FG and h. And so we just kind of sequentially kind of move the derivative through, if you will, and we can kind of extend this product rule. Now, that's cool and fun and great, but let's talk about the quotient rule, okay? The quotient rule is a little trickier, and again, we're not going to get into the proofs of these things because that's not what this class is. If you want to get into the proofs of them, take analysis, which is offered at university level. So quotient rule, which you guys all know, right? I'm not going to have to remind you, right? Quotient just means dividing. So again, we say let f of x and g of x be differentiable functions. Okay. Then d dx of f of x over g of x equals. Now, here's where that order I talked about, with the product rule is important, right? We said the first times the second plus the second times the first. If we think of the first being the numerator, second being the denominator, we get that this is equal to the derivative of the numerator times the denominator. I'm going to put parentheses around this fx to make it really clear. But then minus the derivative of the denominator times the numerator, okay, all over the denominator squared, okay? So alternatively, if j of x equals f of x over g of x, then j prime of x equals f prime of x times g of x minus g prime of x f of x over g of x squared. This is the quotient rule, okay? First times the second, derivative of the first times the second minus derivative of the second times the first. And if you just think first and second, you're like, well, with product, it makes sense. One was listed first, one was listed second. With quotient, just think if you're reading something, right, let's say this, we would read that as 3 over 2, not 2 under 3, right? So we'd say the 3 first. So let's look at an example. Let's look at, this is one that, even if we have a really simple problem, it's still, you're going to need to use the quotient rule, whereas with the product rule, sometimes we could just multiply things out and we'd be good to go. But here, let's let j of x equal 3x to the 4th, and our denominator, let's let it be 2x minus 1. Okay. Again, what I want to do is I want to identify my f prime, my g prime. It's just a really nice thing to do. And I didn't do this the first time just because I didn't have space. I want to write it down this way, and it's going to seem really like pedantic. You're like, God, why are you being so weird? Trust me, this is going to help us out later down the road, writing it like this. So we have our f of x equals 3x to the 4th. F prime of x equals 12x cubed, g of x equals 2x minus 1, g prime of x equals 2. So the reason the way I'm talking about is, kind of writing the original function side by side, the derivatives underneath. We'll get to something later on in this chapter called the chain rule and some other things like that, and it makes this a lot easier when you write it like this, when you understand it like this. So j prime of x is equal to, we know it's equal to f prime of x times g of x minus g prime of x times f of x all over g of x squared. So we just substitute in what we know. F prime of x is 12x to the third. G of x is 2x minus 1. Minus g prime of x is 2 times f of x is 3x to the fourth. And then our denominator is 2x minus 1 squared. Now we just want to combine, we want to distribute and simplify everything that we can. So I get 12x cubed times 2x gives me 24. Wait a second, computer catch up. 24x to the fourth, and 12x cubed times negative 1 gives me minus, minus 12x cubed. And then our 2 times 3x to the fourth gives us minus 6x to the fourth, all over. Now, if you guys aren't comfortable multiplying this out in your head, feel free to write this out as a side project, a scratch work, or anything like that. Do 2x minus 1 times 2x minus 1, use FOIL. But this is going to give us 4x squared minus 4x plus 1. And now we see, is there anything we can combine? I see I have 24x to the fourth and negative 6x to the fourth. So that gives me 18 x to the fourth minus 12x cubed all over 4x squared minus 4x plus 1. Now, there's absolutely no reason to get to this point and try to go crazy factoring, simplifying, doing things like that. And matter of fact, what I would actually recommend doing is leaving the denominator squared. Recommend, unless otherwise told, leave the denominator squared. And the only reason really for that is sometimes the numerator might square out nicely or factor out nicely, you could cancel something like that. But honestly, that's more of a homework type problem. That's more of kind of a situation where it's more of a situation where I would create a problem very specifically so that it does that for you. That's not necessarily something that's going to happen in kind of natural real life situations. So we've got these rules, we've got all this fun stuff, but let's do a problem, right? There's a lot of different ways we could work some of these things and kind of experience their kind of, word problems. But right now I really just kind of want to focus on the process of actually using them. We'll do word problems plenty later. But I do want to bring up one very common word problem that we're going to deal with, and that is velocity. Right? If you all remember, velocity is simply the velocity function is the derivative of the position function. So we let the position of an object on a coordinate axis be given by function s of t equals t over t squared plus 1, where t is the is time. I'll just say time. We'll just be general. We don't need to be too specific. Is time. Okay. Find the initial velocity. Try to clean this up. Okay. So, first of all, what does this mean? What is this? So, initial just means at, right? Oh, this is working great. Input of 0. So this whole question is to simply find v of 0, and remember that that's just simply simple to say, not to write apparently. S. Okay. Glad this is the last one because this pen is annoying me. S of 0. Sorry, S prime of 0. There we go. That's what we're trying to do. So, we know that S of t. Okay, guys, we might be leaving this problem on the cutting room floor because it is not working. Let's see here. S of t equals t over t squared. Plus 1. Sorry if you heard my kids yelling. So, in this case, we're dealing with ft. That's just t. F prime of t is 1. So, bring the 1 out front. We get 1 times 1. Raise the exponent, or drop the exponent down 1. So, we go from 1 to 0. T to the 0 is 1. So, we get 1. So, the derivative of a linear function with a slope of 1 is 1. G of t, t squared plus 1. G prime of t is 2t. This was not too bad. So, means that v of t is working so nicely. Unsaved changes. Yeah, I don't care. Just go away. Just let me write things. There we go. V of t is s prime of t, which is the derivative of the first times this denominator. So the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator over the denominator squared. Now, to simplify this, it's really easy. We get t squared plus 1 minus 2t squared t squared plus 1 squared. Combining like terms, we have t squared and minus 2t squared, so we get negative t squared plus 1 t squared plus 1 squared. Now that is v of t. Okay. That is v of t. But remember, this problem asks for the initial velocity. So that is simply asking what is v of 0. That's negative 0 squared plus 1 over 0 squared plus 1 squared. Well, negative or 0 squared is 0, minus negative 0 is 0, plus 1 is 1. 0 squared is 0, plus 1 is 1, 1 squared is 1. So then our answer would be that the initial velocity is 1 unit, because we don't really have any more, is 1. If we wanted to put units on it, the way we'd have to do it, because it's just moving along the axis at some given time, we would say is 1 unit distance per unit time. But obviously we don't know what the unit distance is, we don't know what the unit of time is, so we don't know if this is inches per second, miles per hour, whatever. And it doesn't really apply because this isn't something moving or something like moving in our real world. This is more so something moving along a number line. Think of it very theoretically. And yeah, so that is it for this section, guys. I don't want to get too crazy with this stuff. I just want to really kind of give you the base rules, kind of how to work with them together, and kind of go from there. You can absolutely apply numerous rules into one problem. And in doing that, you can kind of create different things. I mean, we really did, right? I mean, when we did product rule and quotient rule, we also added in to those the power rule. We added to those the sum and difference rule and the constant multiple rule. All of those to give us our derivatives of the first or second, right? Our derivatives of f and g. And so, yeah, that's it, guys. I just want you to practice this, get really comfortable with these, right? Put this on here in case somebody's not watching these videos and just looking at my notes. Get really comfortable with all of these rules. I don't know why of is not capitalized, but everything else is. We're just going to go with it. All right, you guys. That is it for this section. Hope you guys learned something, took something away. I'll see you guys for 3.4 and 3.5 later this week. And we will be back in person. So this is for winter of 22. So in case I'm using these videos later, we'll be back in person from this brief remote stint next week. So with that, have a good one, guys.